This is the Algebra Semester Exam Review for Unit 2, Topic 2, which is questions 30 through 37. On the semester exam, you're going to be given a formula sheet, so I want to remind you that you have this as a tool, especially, in this topic, we really focus on the recursive and explicit formulas for arithmetic and geometric sequences, so you might need to know this. Question 30. Callie makes a $60,000 starting salary at her new job. She's offered two different options for salary increases. Option A is an increase in salary of $3,000 per year. Option B is an increase in salary of 3% per year. Let the function A of t and B of t represent her salary after t years using options A and B respectively. So the first thing that we're asked to do is complete the tables for each option. Well, as we said, option A is an increase of $3,000 each year. So this is going to become $63,000. And then we're going to add $3,000 again and get $66,000. And then we're going to add $3,000 again and we're going to have $69,000. Option B, however, is an increase in salary of 3% per year. There are a couple different ways you can look at this. What's happening is 3% is 0.03, so we're multiplying by 0.03 and adding that to our previous term. So $60,000 times 0.03 is $1,800. And if we add that to 60,000, we have 61,800. Then if we take 0.03 of that and then add that number to 61,800, we'd get our next number, and so on. What this really is a multiplication of 1.03 every time. So if you think about it, multiplying by 1, that's going to give you your original amount. So 60,000 times 1 is going to be 60,000 again. But since we're multiplying by 1.03, we're getting our original amount plus 0.03 of that amount as well. So really, I'm multiplying by 103% because I'm increasing by 3%. So 61,800 times 1.03 is 63,654. And if I multiply that by 1.03, I'm going to get $65,563.62. There's a formula, if you go back to your formula sheet, that talks about compound interest. Compound interest is A equals P times 1 plus R to the T amount. P is your principal, it's your starting amount. So in this case, we'd have 60,000, and then we'd be adding 1 plus our rate, which is 0.03, to the T amount. So we'd get this formula 60,000, 1.03 to the T amount. If you look at this closely, this is our explicit form for geometric. This is our base, which is our rate, and that is what we're multiplying by every time. So if you know that you're going to be increasing in salary of 3%, you'd be adding 1 plus the rate. If you were decreasing in salary by whatever amount, you'd be doing 1 minus. And that is another way to help figure out what you'd be multiplying by, what the common ratio is. Part B says to complete the recursive rules for each option. Option A is when we increase by $3,000. So our starting amount, A of 0, is $60,000. And our recursive rule, A of t, is always what we're doing to the previous term. Well, my previous term is A of t minus 1, and I'm adding my common difference of 3,000 every time. For option B, my starting amount is still 60,000. But B of t, what I'm doing to my previous amount is I'm multiplying it by 1.03. So 1.03 times B of t minus 1, which is our previous term. So those are our recursive rules. Our explicit rules, well, we already talked about with option B. B of t is 60,000, my starting amount, times my growth rate, which is 1.03 to the power of t. Option A, my explicit rule is my starting amount, 60,000, plus 3,000, my common difference, times t. And again, remember, you have these formulas on your formula sheet, and that will help you. Finally, we're asked to make a sketch of the general shape of the graph. And so if you needed to, you could put each of these in your calculator and look at what the graph is. But remember that these are going to be discrete because we're talking about the recursive and explicit rules. What's happening every year, not in between the years, but at the end of every year. So we know that we're going to be starting at 60,000, so I know it's going to be somewhere above the zero, above the t-axis, and it's going to be going in a straight line because that's what an arithmetic sequence does. Option B, however, we're going to be starting at 60,000, but we know we're just going to be going in a curve because that's what exponential functions do. That's what geometric sequences do. It needs to be discrete. It needs to start somewhere above zero. And option A has got to be a straight line while option B has to be curved. Question 31 says to look at the sequences below. So we have sequence 1, which is f of 0 equals 45, and f of n equals f of n minus 1 minus 4. Sequence 2, which is f of n equals 45 minus 4n, and sequence 3, which is a pattern of 45, 41, 37, 33, 29, 25. We're asked which of the above sequences are arithmetic. Well, let's look at sequence 1. What we see is we have a starting amount, and then we have our previous term minus 4. This means that this is arithmetic. And what it actually is it's the recursive formula for an arithmetic sequence. Sequence 2 has us with a starting amount minus 4 times n. This is also going to be arithmetic. And what it actually is the explicit formula. Sequence 3, let's look at the pattern. 45 to 41, that's minus 3. 41 minus 3 is 37, minus 3 is 33, minus 3 is 29, minus 3 is 25. So this literally is an arithmetic sequence. Therefore, our answer above is D, sequences 1, 2, and 3. Question 32. Frida is keeping track of how many coupons she has saved on a piece of paper. She spilled some coffee on the paper. Her list now looks like this. She's got this stain, which represents where the coffee spill occurred. So she knows she started at 30 coupons, but after 1 week, some number of coupons, we're not sure what it is. After 2 weeks, we have some number of coupons. After 3 weeks, we have 240 coupons. Part A says, assume that the sequence of the number of coupons is arithmetic. How many coupons did she have to have after week 1, and how many did she have after week 2? Well, let's start writing this out. We know we're going to have 4 numbers for the 3 weeks and what we started at. We started at 30, we ended at 240. We know it's going to be arithmetic, so we're going to be adding by a common difference every time. And if I start at 30 and I add 3 D's, I'm going to get the number that equals my last spot, which is 240. So the first thing I'm going to do is solve for D. So I have 3D equals 210. Divide by 3. D is going to equal 70. That means plus 70, and 30 plus 70 is 100. And then 100 plus 70 is 170, and 170 plus 70 is 240. So how many coupons did she have after week 1? She had 100. How many coupons did she have after week 2? She had 170. Our next part, part B, says that we should assume that the sequence of the number of coupons is geometric. So we're going to still have our 4 spots. We're going to start with 30. We're going to end with 240. But now, since it's geometric, we're going to be multiplying by our common ratio. So I know that 30 times r times r times r is going to equal 240. Well, this is 30 r to the third, which equals 240. And the first thing I'm going to do is divide both sides by 30. So I'm going to get r to the third equals 8. And what I know is r to the third also equals 2 to the third, because 2 to the third equals 8. Since they have the same exponents, r must equal 2. So that means that we're going to be multiplying by 2 each time. 30 times 2 is 60. 60 times 2 is 120. And 120 times 2 is 240. So she had 60 coupons after week 1 and 120 coupons after week 2. Question 33. In art class, students create a project with blocks and a pattern. Students will use algebra to describe the pattern. A student writes 2 formulas on the board. So we have the recursive formula at f of 1 equals 3 and f of n equals 2 times f of n minus 1, and the explicit formula, f of n equals 3 times 2 to the power of n minus 1. Write the first 5 terms of the sequence. So we're going to have 1, 2, 3, 4, 5 terms. Our first term is 3. And then what we can see from our recursive formula is that every time we're going to be multiplying by 2 to our previous term. So 3 times 2 is 6. 6 times 2 is 12. 12 times 2 is 24. And 24 times 2 is 48. And those are our first 5 terms of the sequence. Next, it asks, you want to know the value of f of 30. Is it more efficient to use the recursive or explicit formula? Explain your answer. Now, they bold and underline more efficient for a reason. Can you use either formula to get f of 30? Absolutely. But which is going to be the more efficient one to use? So, it is more efficient to use the explicit formula. This is because I just need to substitute $30. So I just need to substitute 30 in for n and simplify when I use the explicit formula. However, if I was to use the recursive formula, I would have to find, sorry, I don't know what happened. I would have to find the previous 29 terms in order to find the 30th term. Which is far more inefficient. So it's more efficient to use the explicit formula because I can just plug in 30 right here for n and do 2 to the power of 29 times 3. If I was to use the recursive, I need to know the previous term and multiply it by 2, which means I need to know the 29th term to find the 30th term, which means I need to know the 28th, 27th, 26th, 25th, and so on. I'd need to find all 30 terms in the pattern to find f of 30. Question 34. Julio is filling out his tax return. He needs to report the value of a computer that he bought several years ago for $8,192. He has two options for doing this. Option A is the value of the computer decreases every year, so its value is 3/4 or 75% of its value from the previous year. Complete the recursive formula for the value of the computer using option A. So they give us our starting amount, A of 0 equals 8,192. And then we have to find A of n. And remember, we take our previous term and what we do to it. So if it's decreasing by 3/4, we'd either have 3/4 of A of n minus 1, which is our previous term, or we could have 0.75 times A of n minus 1. So either one of these works, they mean the same thing. After 2 years, how much will the computer be worth using option A? Well, we have 8,192 as our starting amount, so we need to find what our amount after year 1 would be and our amount after year 2. So I'm going to multiply by 0.75. 8,192 times 0.75 is 6,144. And 6,144 times 0.75 is 4,608. So it will be worth, it will be worth $4,608. Option B says the value of the computer decreases by $1,024 each year. Complete the recursive formula for the value of the computer using option B. Well, again, the recursive formula is what we're going to do to our previous term. We've started with our initial amount, and we're going to take our previous term and subtract 1,024 from it each time. After 2 years, how much will the computer be worth using option B? Well, again, we're going to start with $8,192, and we're going to see what happens after year 1 and then year 2. But this time, we're going to be taking away $1,024. So 8,192 minus 1,024 is $7,168. And then we're going to take away 1,024 again, and 7,168 minus 1,024 is 6,144. So it will be worth $6,144. For the last part, after which year will the value using option A be greater than the value using option B? Complete the table below. So A of n, so this column right here, is where we're going to be multiplying by 0.75 each time. So 8,192 times 0.75 is 6,144. 6,144 times 0.75 is 4,608. That number times 0.75 is 3,456. Times 0.75, we have 2,592. Times 0.75, we have 1,944. Times 0.75, we have 1,458. Times 0.75, we have $1,093.50. And if we multiply that number times 0.75, we have $820.13. However, B of n, the second column, is when we're going to subtract 1,024 each time. So 8,192 minus 1,024 is 7,168. Minus 1,024 is 6,144. Minus 1,024 is 5,120. Minus 1,024 is 4,096. Minus 1,024 is 3,072. Minus 1,024, we have 2,048. Minus 1,024, we have 1,024. And 1,024 minus 1,024 is 0. So after which year will the value using option A be greater than the value using option B? And that's going to be right here. So after the seventh year, the value using option A will be greater than the value using option B. Question 35 says to use the answer bank below to complete the following statements. A. An explicit rule for an arithmetic sequence would be called a linear function. The recursive formula f of 0 equals 20, f of n equals 30 times f of n minus 1 represents a geometric sequence, and its explicit rule would be an exponential function. The sequence 10, 12, 14, 16, 18, 20 has a constant difference of 2. We know this because it's adding 2 every time. And the sequence 10, 20, 40, 80, 160 has a constant ratio of 2 because it's multiplying by 2 every time. Question 36. An office is interested in how much recycling occurs. On the first day of a month, there were 700 pounds of recycled materials. Each day after that, 80 more pounds of recycled materials were added. Let R of n represent the total number of pounds of recycled materials on day n. Complete the table for the total number of pounds of recycled materials. So we know that we're adding by 80 each time. So 780 plus 80 is 860. 860 plus 80 is 940. 940 plus 80 is 1020. And 1020 plus 80 is 1100. Our days are increasing by 1. So 2 plus 1 is 3. 3 plus 1 is 4. 4 plus 1 is 5. And 5 plus 1 is 6. And that's our table. Next, we're asked, on which day will there be 1,580 pounds of recycled materials? Show how you determined your answer. Well, you can very much continue the table, keep adding 80, and figure out how many you have. Another way to do it is to find the explicit formula. Well, we know that this is arithmetic because we're adding by 80 each time. So I'm going to find the explicit rule. And I know that my explicit rule is going to be R of n equals my starting amount. I should put not F, sorry. R of 0 plus D times n. All right, so D being my common difference, which is 80, so 80n, and R of 0. Problem is that we have R of 1 right now. So to find when n equals 0, we have to take 80 away from 700, and this is going to give us 620. So my explicit rule is 620 plus 80n. Well, I want to know, when will we have 1,580 pounds? So 1,580 pounds equals 620 plus 80n. I'm going to subtract 620 on both sides and get 960 equals 80n. I'm going to divide by 80, and n is going to equal 12. So this is going to be on the 12th day. On the 12th day, there will be 1,580 pounds of recycled materials. Next, it wants us to write a recursive formula for the number of pounds of recycled materials. Well, here that they're starting with R of 1, which we know is 700. And then R of n, it's what we're doing to our previous term. So R of n minus 1 is our previous term, and we're adding 80. Part D asks us to write an explicit formula for the number of pounds of recycled materials. Well, that's what I did in Part B, so I can just say 620 plus 80n. Question 37. Look at the pattern of small squares below. The number of small squares n of t is a function of the figure number t. Part A wants us to draw the pattern for figure 5. Well, in figure 1, we have 1 block. In figure 2, we have 2. In figure 3, we have 4. And in figure 4, we have 8. So, hopefully you can see that the pattern is multiplying by 2 each time, which means that we're going to have 16 blocks in figure 5. So one way to draw this would be to have all of them on top of each other. That's 2, 4, 6, 8, 10, 12, 14, 16. Another way is we could have it as a 4 by 4 square, which is also 16. Either way, as long as there are 16, you're good to go. Part B says to complete the table for figures 1 through 7 for the number of small squares. So we know that for figure 1, we had 1 block. Figure 2, we had 2. 3, we had 4. 4, we had 8. 5, we had 16. And we figured this out because we were multiplying by 2 each time. So 16 times 2 is 32, and 32 times 2 is 64, and that's our table. Part C asks us to make a graph for the number of squares. So using that table, when there was 1 figure, we had 1 block. When there were 2 figures, we had about 2 blocks. Figure 3, we had 4 blocks. Figure 4, we had 8 blocks. Figure 5, we had 16 blocks. Figure 6, we had 32 blocks. And figure 7, we had 64 blocks. So this is what your table or your graph should look like. All right, Part D says write the recursive formula for the sequence of the number of squares. So writing the recursive formula, they have n of 1, and that was our starting number, and we had 1 block. We know that we're multiplying by 2 every time, so we're going to multiply 2 times the previous term, which is n of t minus 1, and that's our recursive formula. When we write our explicit formula in Part E, we have to remember that we should be starting with n of 0, not n of 1. So we know that if n of 1 was 1 block, and we're multiplying by 2 for every previous term, that means that we're dividing by 2 to go backwards. So n of 0 is going to be 1/2. So our explicit formula is our starting amount, which is 1/2, times our common ratio, which is 2 to the power of t. So that is our explicit formula. Finally, Part F is the sequence of the number of squares arithmetic, geometric, or neither. Explain why. It is a geometric sequence. And this is because there is a constant ratio of 2. So it is a geometric sequence because there's a constant ratio of 2. And this ends Unit 2, Topic 2 of the Algebra 1 semester exam review.